So I thought it would be a nice, nice to try CoCalc for a semester and see how it goes.
And sound if there's like a way to do it offline and then you can upload it after you get back online, or is it always required to be online constantly?
That's a good question. I don't know how much you could do offline.
But then you could probably, well, I'm wondering then, like, you could do Octave if you aren't online and then you're online.
I mean, you can always download Octave as a standalone app on your computer and just use it there. But I want to put stuff up there because I can do demos easier, I think, on CoCalc.
Okay.
And stuff like that. And, you know, sharing code and stuff is easier on CoCalc.
Yeah, we'll probably have them.
All right, well, so anyway, I'll have more information later as we get closer to the end of the semester on that. But, anyway, so today I want to talk about magnetic resonance. So this is so again, this has to do with, you know, if you go to the hospital and you get an MRI, that's magnetic resonance. It deals with the hospital MRIs deal with the proton itself. So you're looking at the magnetic resonance of the proton. So for medical MRIs. That's the proton resonance. So you're looking at water basically. So depending on, you know, the tissue that the water is in, like if it's in a muscle or if it's in a tendon, those kinds of things, it changes the way that the water interacts with its surroundings, and so the NMR picks that up really easily, and that's how you get really nice, high quality images of NMR or MRI. So let's stick with proton resonance, and we'll just think of the proton as a spin 1/2 particle. So you know, there are two states. It can point up or it can point down, and so I want to pause for a moment and talk about the classical description of magnetic resonance. So classically, it's a little bit, there's a lot going on here, so I want to talk about it classically first. So we have, there's a large external field. So we can call this the z direction. So we can call this B0 in the z direction. And this field is very large. In fact, you want to make this field as large as you can make it. So that's why big MRIs are expensive. It's because to try to make this field as big as possible. And then you have a coil here that has its axis along the x direction. And in this coil, you'll run a current that has this thing is proportional to some cosine of omega t. Okay, so it's an oscillating current. And so in the field, so in the external field, there's an energy for the particle that's minus mu dot b zero. And so that being spin up or spin down, you can, you have two states in this, there are two states in this field. Okay, and so what, if I have a strong field, under a strong field, the spins align with the field. So let's say we have this B0 field here, which is really strong, then I'll have, if we have a number of protons, they'll align with the field. Okay, so these are just, individual spins. But now let's, what happens when we put on this field B1 in the x direction? So next we apply a field B1 x hat. And so there's a force to align the field, or align the particles, align the spins with B1 x hat. Okay, they tip. Okay, so they'll start to, if this is my spin, here's B1 x hat, I've got a field in that direction, and the spin tries to tip in the direction of the field. Okay, so once the spin begins to tip, it begins to precess around and from the B1 field. Or sorry, the B0 field. Okay? So because B0 is really strong, what happens now is, now you've got this spin and it's tilted. So this is that's the x direction. And now you've got a precession around, whoops, that's way too big of a. Okay, the spin starts to precess now because it's tipped in the big B0 field. It starts to precess around that field. Okay, and that's the same reason that a top precesses on a, if you put a spinning top on a table, it precesses, if it's not straight up and down, if it's tilted, it will precess because of the magnetic field puts a torque on it, and because of the conservation of angular momentum, you get the precession. Okay, so that's what happens here. So the goal then is is to tune omega so that the following situation occurs. So at, let's say t equals, 0, I have my spin is pointed like this is the x direction. And so it's tilting this way. And this is B1 in the x direction. But remember, this current goes both ways here. So after a half period, at t equals t over 2, we have B0 x hat, we have the field pointed in the other way, and this spin has precessed around so that it's the tip is at the other in the other direction. Okay, so now that it's tilting, it wants to tilt again this way. Okay, because of the sorry, not B0, B1. This is B1. Okay, does this make sense? Yeah.
So you want the frequency of your alternating current to match with the frequency of the precession?
Yeah.
Okay.
So that you have the force where you're trying to tilt this spin toward the x-axis is you're always catching it at just the right time as it goes around. So what happens? So in the field, the classical picture is that the spin does this. It tilts, it's precessing, and it tilts more and more down to the x-axis. Okay, so that when after a certain amount of time, it's completely tilted. Okay. Then after is in the xy plane. It's pointed along x. X hat and minus x hat, it's precessing. What is in the xy plane? What's this? X hat, y hat. And we already investigated what happens if we put a spin in a z direction. It just precesses around it. So if it's in the xy plane, it's just now it's just precessing in the plane. Okay. Now this is like the spins themselves. They're little bar magnets. Okay. So once you've done that, so now you turn off the current. You're not going to drive the current anymore. But the spins themselves are little bar magnets, and they're little bar magnets that are moving around like this in the field. So they're going to, these are coils of wire. So you've got now you've got a B field that's going like this inside this coil of wire. So they're going to generate a current in the wire. So as the spins are going to relax. And when they do, they generate current in the coil called the free induction decay. Or FID. And so if you look at the current in the coil, it does something like this. Okay, and so from the free induction decay, there's just a tremendous amount of information inside the free induction decay. So, analyzing that, then if you're an NMR expert, analyzing this free induction decay, you get into a whole lot of very sophisticated signal processing and stuff like that. But that's the basic idea. That's how NMR works. That's how magnetic resonance works. MRIs are a little bit different because in an MRI you want spatial information, and so it doesn't work exactly this way. So, in MRIs, you have the magnetic field is not constant. And
you have to generate that as well, right?
Right, but the point is there that you, like here, you want B0 to be as uniform as it can be. In a magnetic resonance imaging, you don't. You actually have a gradient, a strong gradient in the field. Okay, so, but anyway, that's beside the point. So, so that's the general picture of how magnetic resonance works classically. So now let's think about it quantum mechanically. And so to do this, I want to talk a little bit more about some thermodynamics. So, so let's consider a particle with two possible states. With energies 0 and epsilon. And then consider and connect this particle to a reservoir. So here's the picture. We have some reservoir, and then we have a particle that's connected to the reservoir, and it can take two energies. It can be 0 or epsilon. And the reservoir has some energy E, and the number of states G. So, okay. So give me some energy that you have that's in the reservoir, and there are some number of accessible states. So if I consider the probability of a particle being in the state, it's connected to the reservoir, it can exchange energy with it. That's why I drew it that way. Particle can exchange energy. With the reservoir. Then the probability, the ratio of probabilities of the particle being in in state epsilon or 0 is we can write that ratio of states, ratio of probabilities, should be proportional to the number of states that the reservoir has at those two different energies. So if I'm in state of energy epsilon that had to come from the reservoir, so this has to be E minus epsilon. And then this is, if it's in state of energy 0, then the reservoir has its full energy. Okay? Now, for when we define the entropy, we want it to be additive. For composite systems. So let's define sigma, which will be the entropy, as the log of G. That makes it additive if I put two systems together. And so G then is equal to E to the sigma, and the ratio of states is P of epsilon over P of 0. That has to equal, so G is E to the sigma, so this is E to the sigma of E minus epsilon over E to the sigma of E. And if epsilon is small, which we assume it is, the reservoir is always bigger than our little subsystem. So we can expand sigma of E minus epsilon just as a first order Taylor series. So this will be sigma of E minus epsilon d sigma dE. And we can plug that in here. So we'll have P of epsilon over P of 0 is E to the sigma of E, E to the minus epsilon d sigma dE over E to the sigma of E. We can make some cancellations here. And then we can write P at epsilon, the probability of, and epsilon is the probability of being in state 0 times E to the minus epsilon over tau, where we define tau is equal to d sigma dE. This is the dimensionless temperature. Okay. So now we use probability conservation here. So we know that P of 0 plus P of epsilon, that total probability has to be 1. It has to be at one state or the other. So then we can write P of 0 plus this, which is P of 0 e to the minus epsilon over tau equals 1. And so P 0 is equal to 1 over 1 plus e to the minus epsilon over tau, and then finally P of epsilon is e to the minus epsilon over tau divided by 1 plus e to the minus epsilon over tau. Okay, so this is for, boson, or fermions. This is the fermion rule. And one of the things, so the important piece here that I want to focus on is just the fact that it's proportional to e to the minus epsilon over tau. So Okay, so that means for any two, let's see this. Leave it up there. Um, This is just, this gives us the Boltzmann distribution. Okay? So that means even in a very strong field, some spins will not be aligned. With the field, and that's why you go for really high fields. So the more, the higher strength your external field is, the more of those spins you can get aligned with the field, and the higher the signal that you'll get in your free induction decay. Okay, but there's always a population that's just, not gonna play along because it's just, that's the thermodynamics. Okay, so let's do the quantum mechanics now of magnetic resonance. So before I do that, are there questions about anything so far?
I'm just curious if you could explain dimensionless temperature as a concept to me.
Well, so dimensions are really, as experimentalists, you use dimensions all the time, but if you're studying something sort of from a theoretical perspective, dimensions just get in the way, and so you try to eliminate them.
Okay.
So for example, in high energy physics, it's common to set c equals to 1, the speed of light.
Mm-hmm.
So that means that, if I had a meter stick that was big enough, or it wouldn't be a meter stick, it would be some other stick, c would be 1.
Right. Just one speed of light.
Yeah, like, so after if a second passed by, the light will have gone the length of 1. So my meter stick would be, 300 and some thousand miles or something.
3 times 10 to the 8.
Yeah, 3 times 10 to the 8 meters.
Was it also energy is a dimensionless, quantity, isn't it? Or I'm thinking of dimension wrong.
Well, we're making C, this just simplifies conversions basically, right? So if X is equal to CT, if I'm using units where C is 1, then X is just equal to T, but if that's the case, then then you can say like X and T have the same dimensions, time and space and things like that. So in here, we're defining this quantity sigma, which is just a log of the number of states of the system. So This is, Boltzmann's formula is S is equal to K log W. You've probably seen that one. That's KB. So we're just setting KB equal to 1.
Oh, I see. Okay.
Okay.
Yeah, that goes back to setting that constant to 1.
Okay.
Okay, so let's do the quantum mechanical analysis of this magnetic resonance. All right, so we saw before that H, when we had for just a B field, was for a B field along Z. But now we have a field along X, so we'll write H is equal to omega 0 S Z hat plus omega 1 cosine omega T S X hat, where, so omega 0, remember we defined this as, it was E times G times B0 over 2MC. And omega 1 will be EG B1 over 2MC. So this is the, B0 again is the field along the Z direction, it's the strong field, and B0 is this is the weak field. Okay, so we have B1 is much less than B0, so we have omega 1 is much less than omega 0. Okay, so now let's write the, so SZ hat, we'll just use our representations of SZ hat and SX hat. So if we plug those in now to our Hamiltonian, so then we'll have omega 0, h bar over 2, 1, 0, 0 minus 1 plus omega 1 cosine omega t Sx, which is h bar over 2, and then 0, 1, 1, 0. So we can just put these two together. So we'll pull out an h bar over 2, and then we'll have omega 0 here, and then we'll have omega 1 cosine omega t, omega 1 cosine omega t, and then minus omega 0. So that's the Hamiltonian for the system. now we have h hat is explicitly a function of time. Okay, so that means we can't use the time evolution operator.
And I just learned that.
Yeah. It still comes in handy though, don't worry. Okay, so that's a bit of a bummer, but you know, we can still solve the problem. We just have to now go and actually solve the differential equations. So this is just okay, so we must just solve the Schrödinger equation directly. So let's just write it down first before we do anything. So if we're going to solve the Schrödinger equation, this is IH bar psi of t is equal to h acting on psi of t. Okay, so let's work in the z basis. Okay, this is already in the z basis anyway. We took both of these operators are expressed in the z basis. But let's write psi of t. We don't know what it is, but so let's just write it as some coefficient a of t times z plus b of t times z minus. So if we, in our column vector format, this is just a of t, b of t. Okay, everybody cool with that? All right, and then let's let time derivatives be dots. Okay, so we'll try to use some compactifier notation. Whoops, there's a time derivative up here. So this is
I thought there was a derivative there.
Take the time derivative of it. Okay, so let's just plug everything in and see what we have. So if we write it out, we'll have I h bar, and then we have a dot. I'm not going to keep writing they're functions of time. I don't want to keep writing out the functional dependence. And this is equal to h, which is h bar over 2. And now we have omega 0 and omega 1, cosine omega t, omega 1, cosine omega t, and minus omega 0. And that's just acting on A and B. Okay. All right, so let's just write them out now. Let's write the equations out. This is 2 equations. So if I drop my h bars, bring my 2 up to the left-hand side, then I'll have 2i a dot is equal to omega 0 a plus omega one cosine omega TB, that's one equation. And then I'll have two I B dot is equal to omega one cosine omega T times A minus omega zero B. Okay, so these are two equations we have to solve. They're coupled, and they're not easy like before, because now we have cosines here and here, which make it harder to solve. So the approach to solve this is to first work out, we want to simplify the solution. So let's eliminate some of the dominant behavior. Due to omega zero, which is much greater than omega one, okay? Because we already said that, the field, this is the weak field B1 by comparison. B0 is a much, much stronger field. So in our equations here, we can simplify them a little bit by just first assuming that omega 1 is equal to 0 and seeing what the dominant behavior is. So if we do that, so let omega 1 equal 0, and then we'll have the following equations. We'll have 2I A dot is equal to omega 0A, and then we'll have 2I B dot is minus omega 0B. Okay, now these are simple equations. So what are the solutions to these equations?
This is the exponential.
Hmm?
It's the exponential.
Right, exponential. I've got the time derivative is equal to just some constants times the function itself. So we have A is proportional to e to the, let's see here, minus I omega t, omega 0 t over 2, and B is proportional to e to the plus I omega 0 t over 2. Right, because I bring this I over here, that's a minus I. Right. Okay, yeah, question?
Oh, no, no.
Any other any questions? Okay, so A and B are proportional to these things because omega naught is so large. So now let's redefine some things. So now let's let A of t be equal to some, let's see, A, B, C, and D, A, B, C of t e to the minus I omega 0 t over 2, and B of t equals D of t e to the plus I omega 0 t over 2. Okay, so what we've done here is we've said, this is sort of saying, I know A is behaving like this, so let's let that be the dominant behavior, and then we'll put in some other C of t here, and then what I can do is plug these back into this set of equations, and I can find differential equations for C and D.
Actually, so I do have a question.
Yeah.
So why did the two got divided into the superscript on the exponential, but I got turned into a negative?
Well, it goes, I'll have, if I bring this I to the other side, it's a minus, right?
Isn't it multiplied by a, so wouldn't it be divided?
Well, I divide, 1 over I is equal to minus I.
Oh, okay, gotcha.
Any other questions? Okay, so let's plug these. Into these equations up here, star. 2I A dot. A dot now is C dot e to the minus I omega 0. T over 2 plus C, oops, minus C, right? So it's I omega T, I omega over 2, I omega 0 over 2, e to the minus I omega 0 T over 2. Okay, that's all right. And this has to equal omega 0 A, which is C e to the minus I omega 0 T over 2. Plus omega 1 cosine omega T. And B, which is D e to the plus I omega 0 T over 2. Okay, is that right? Did I make any mistakes? And then the next equation is 2I, and this will be d dot e to the plus I omega 0 T over 2 plus d I omega 0 over 2 e to the plus I omega 0 T over 2 is equal to omega 1 cosine omega T C e to the minus I omega 0 T over 2 minus omega 0 D. Okay,
You said omega 1 was 0 though, right?
what's that?
You said we defined omega 1 as 0, right? So those terms
No,
are.
no, no, after, we only did that here just to determine this behavior.
Okay.
And now when we use these equations and plug them back in, omega 1 is back to just being
Okay.
something non-zero.
Okay.
Okay, so I should have some cancellations here. So, okay, up here, what do I have? I've got C e to the minus I omega 0 T over 2 times omega naught. And this term here, this 2 will cancel this 2. This I will hit this I and give me a plus 1. And I'll have C omega 0 e to the I omega T over 2. So I can cancel this term with that term. And then likewise down here, I can cancel this term with this term. I'll have omega 0 minus omega 0 d. So I can cancel this term with that term. Okay, so what do we have? We've got, let's see, I'll write this one more time. 2I C dot e to the minus I omega 0 T over 2 is equal to omega 1 cosine. Let's write the cosine as e to the I omega T plus e to the minus I omega T over 2. That's just the cosine. Times e to the I omega 0 T over 2 times d. the second equation will be two I d dot e to the plus I omega 0 t over 2. And that will be equal to omega 1, and we'll again write the cosines, e to the I omega t plus e to the minus I omega t over 2 times e to the minus I omega naught t over 2 times c. Okay, I can bring this e to the minus, I can bring this to the other side. That will make this on the right side e to the plus I omega naught t. And I can take this to the other side, and that'll just make that a full e to the minus I omega naught t. So if I rewrite these equations again, I'll have 2I c dot is equal to omega 1 over 2 and then I'll have here e to the I omega plus omega 0 t plus e to the minus I, I'll have omega minus omega 0 t times d. And then the bottom equation will be e to the I omega minus omega 0 plus e to the minus I omega plus omega 0 t times c. Okay, so we have these. We have those equations finally. Now now we want to just imagine, we want to imagine that we're integrating these equations to find C of t, right, and D of t. So imagine.
I think you mismatched the parentheses there.
Hmm?
You mismatched the parentheses in the bottom line.
I did.
The I on the bottom line, the I parentheses omega minus omega, not put the t inside of parentheses.
Oh, thanks. Very good. Thank you. Okay, so now imagine integrating, and this is, now it's hard for you to imagine this because you haven't taken a numerical course and learned how to integrate functions or anything numerically. But if you integrate a function numerically, you actually just step along and you integrate it, you sum it up just like you would like a Riemann sum. So if you were to do that, you have to imagine when you integrate these things, what part of the integral is going to give you the most, what the most contribution, the biggest contribution, and what part of the integral is going to give you the least part of the contribution. So if you look at the terms here, which terms can I just ignore when I integrate? This isn't necessarily an easy question, so.
Depending on how close omega and omega 0 are, right?
Yeah.
If omega is very, very, because if that term there is 0, then no, that just means e equals 1.
Yeah. That's good. Keep going.
Okay.
you're onto something there, so what is it?
I don't know, I was thinking that like, cause I don't really know what omega and omega zero are, but.
We can, basically, he's hinting at that we can ignore omega zero, right, we can like,
Right.
it's not gonna
Omega zero is
contribute
small.
that much.
If omega zero is very small, then we can get rid of it, but if omega zero is very close to omega, then that whole, exponential there has to be one.
Yeah, well, that's a good thing though, isn't it?
Yeah.
Why is that a good thing?
Makes it easier to integrate.
Yeah.
I was
Well,
trying
it's
to see
also
if it.
big, right?
Right.
What happens if, what happens if omega and omega zero are both large?
Oh, then that goes to, then that exponential becomes very big, if they're both big. Well, actually, no, we don't, there's a minus sign there. Well, if they're both large, then. If they're both
Then-
large, then the exponential with that's negative would go to zero.
The exponentials have eyes, so they don't get very big.
Yeah.
What do they do instead?
They alternate, they,
Oh, yeah.
Right, they oscillate.
oscillate, that's the word.
Okay, so when omega, and these are, these frequencies are fairly large. So these are big numbers. So when omega and omega naught are both large, this thing oscillates very quickly as with t. And it just goes positive, negative, positive, negative, positive, negative. It just cancels itself out. So it doesn't contribute much to the integral.
Yeah.
Okay, so if we're integrating C and D, we can ignore terms with omega zero plus omega. Also because, not just because it oscillates, I mean, it does. But also as we discussed earlier, the operator tries to tune omega to omega zero so that you get the tipping. The classical tipping anyway. So that means we can just ignore those terms. Thus we have 2I C dot is equal to, I can ignore this term completely. If omega is equal to omega zero, we'll have omega 1 over 2 D, and 2I D dot is equal to omega 1 over 2 C. Okay, so now we have some really, simple things we can work with, right? So I can take the derivative of the top. I can write, first of all, just solve for C dot and take the second derivative. So I'll have C double dot is equal to minus I omega 1 over 4 D dot. But D dot is just, that's minus I omega 1 over 4. D dot is, it's minus I bring it over there, and then I'll have another omega 1 over 4 C. So this is, so C double dot is equal to omega 1 over 4 squared C. So we have then, and that's this, these things are structurally identical, so it's the same for D. So we have, let's define omega tilde is equal to omega 1 over 4. Then we have C of t is equal to some A cosine omega tilde t plus
Should that be
B
negative?
sine omega tilde t. Okay, and the same for D. So now we found C and D. So let's go ahead and, wait, there's a minus. There's a minus on here, I've got two i's give me a minus. So that gives me, that this is sines and cosines, and then so we can write this down. Okay, so that's our solution. So, what did we have? We have that psi of t was equal to, it was a of t, b of t, but a was c of t e to the minus I omega 0 t over 2, and this was d of t e plus I omega 0 t over 2. So now we have to put in some initial conditions and then just solve for the behavior. So let's put in psi of at time 0 is 1. So this means this is in we start off in the z plus direction. Okay, so at time 0, that means we need c of 0 equals 1. That means we can let a equal 1, and if at the very top here, we expect c prime at time 0 has to be 0, so b will be 0. Capital B will be 0. Okay, so we have some simple motion. Okay, so that means that psi of t is equal to cosine omega tilde t e to the minus I omega 0 t over 2, and d will be sine omega tilde t e to the plus I omega 0 t over 2. Okay, and that we can get that from this equation here. So if c is a cosine, then d will be a sine. So what happens then? This means that the probability of, this is something we've kind of seen before. We have this is the probability for finding z plus, and then this is the probability for finding z minus as a function of time. These amplitudes are, for z plus will be cosine squared omega tilde t, and this will be sine squared omega tilde t. Okay, so this means that we have our two states, and there's an energy level between them. So this is spin up. So we have this big external field, and this is spin down, and transitions occur when B1 is turned on at the frequency omega equals omega 0. Okay, and the energy of the state difference here depends on this frequency. Is it time? Okay, so the difference between the quantum mechanical and the classical picture of magnetic resonance is the following. In the classical picture, you think of the spin as tipping in the field as your oscillating field is turning that B field around in a circle, right? So you think of it as tipping the field down to the plane where it's oscillating around, and then you let it relax back and you get your FID. From the quantum mechanical perspective, you just have two populations. You look at the Boltzmann distribution and you have two populations depending on the temperature. And when you turn on the field, you equalize the populations because you cause transitions between the two. And so you just get a 50-50 mix of the spin up and spin down, which is the same thing, incidentally, as being in the X. Remember, X is equally Z plus and Z minus, right?
Mm-hmm.
So the classical picture fits in with the quantum mechanical picture, but the quantum mechanical picture is the one that is the more correct one to think about. So you have the population that depends on the temperature, so you'll have a bunch of them aligned up here, for example, but then you can equalize them to 50-50 by turning on the oscillating field, and then you can let them relax back after you turn off the field. So. Are there any questions?
Not gonna lie, I was thrown off entirely by the dividing by eye thing. I don't know how I made it this far without knowing that.
Oh.
I knew about this, like there's like the I to the 1 to the 2 to the 3, like there's that pattern. Apparently it also extends downward. I was never taught that. It makes sense now.
Good. Learn something new every day.
Yeah.
So classically, the spinning bars force the current and the coil. What is quantum mechanical explanation for that?
Oh, let's see. I think that's a hard one to answer. I think it has to do with, there's photons will be emitted when you jump from one state to the other. So when it's relaxing. So there's going to be photons in the cavity. And when the numbers are large enough,